try to keep. And you need, whoops. Go ahead and clear the instruction format or your textbook, one or the other. So I have fewer of these. I don't have 2 spares. All right. So what I want to do with this is do what an assembler does. I'm going to talk about how this goes. So we were working on this and we got down to the storage allocation directives. So you should have addresses up to line, say, 22. You have that, yes? Okay, good. So if the address of alpha is 002B, then what is the address of beta? Okay, well, what's this RESW on line 22? This is reserved word. So we have 4 assembly directives that we need to remember. All right. Reserved byte, reserved word, and then there's a quantity. How many of them? Then byte and word, which take constants. Okay. Line 22, alpha, reserved word 100. Note that this is in lowercase, and this is just to show you that it's not case sensitive, it doesn't matter. So somebody tell me the address of beta. What is the address of beta?
Okay.
What's that?
Can I get one of them?
One of these. All right. Nobody?
800.
Alpha plus 300. Yes. Okay. Huh. Okay. Does everybody know where this came from? Where did that 2B come from? Does everybody know?
Last time.
That was from last time, and we're just going along. So the first line that has an address that's not 0 is which line? 8. 8 is 3, 9 is 6, so it's the size of the instructions that dictate the address. So we marched along adding either 1, 2, 3, or 4 to each instruction as was appropriate. Well, you can tell how big they are by looking on this chart. You can look. LDB is 3, LDS 3, plus LDX 4, plus LD3 4, add 3, LDX 3, plus LDT 4, and so on. Everybody's got that, right? So we have a simple arithmetic problem here. Do I want to do this? Oh, heavens no. Well, what's wrong with doing that? We said it's 100 words, and each word is 3 bytes. That's 300, isn't it? Huh? That's base 10. We have one number in base 16 and one number in base 10. Oops, not so cool. All right, what do you want me to write then?
Divide 300. Convert 300.
What's that?
Convert 300.
Okay, go ahead.
300 divided by 60.
Yes?
0012 C.
1, 2, B?
C. 12 C.
That doesn't sound right. Might be. Well, what's 300 in hex? Now, I don't know off the top of my head, but I know what 100 is. It's 96 plus 4. 6 times 16 and 4. That's 100. So that is C8. I mean, you can always figure this stuff out, right? 8 and 4. C and 6. What's 12 and 6?
18.
Do we agree? Okay, so this is 256. 1 times 16 squared, 256 plus 32 plus 12. Is that right? 6 and 4 are 10. 8, 9, 10. Wow, that's 300. Is that what you told me before? Yes, okay. 1, 2, C. Okay, so you guys are going to have to do this, so you should be familiar with it. I know you learned this in 237. Some of you left the class and never thought of it again, but you're going to need to do this. So does this seem like a really hideous thing to ask you to do? There's worse. There's worse. Anybody in 560? They're going to ask you to do worse.
Never.
Yes? Okay, B plus C. Now my brain doesn't work that way. I've been doing this a long time, but my brain still does not say B plus C. So I write it off to the side. I know B is 11 and C is 12. Now if you don't know that, you better do some reviewing. You will get bit. You should know that. It may not come instantly, but you don't get brushed up, get familiar. Okay, so this is 23. B plus C, 11 plus 12 is 23. Well, I can't write 23. Well, there's no digit for 23. So I'm going to have to carry, and what am I going to carry? I'm not carrying 1. I'm not putting 22 here. No, I'm carrying 16. Yes? Yes. So I'm going to take 16 out of that, which leaves me with 7. So now we're on 157. So because addresses are 5 bits, that's why I've written 5. But where you have lots of even zeros, it's not critical. Okay, that's the address of beta. Now what's the address of gamma? What's the address of gamma? We can all do this, yes? Because beta is also reserved word 100. So, 12 and 7. 12 and 7. 19. 283. Did I have that right? I didn't know to make arithmetic mistakes. I think I was asleep in 3rd grade. Yes?
Is there a reason why it's capitalized now?
It doesn't matter. The reason I made them different is to point out that fact, that the assembler is case insensitive. All right, 12 and 3 are 5, which is, I'm sorry, 12 and 3 are not 5 but 15. Yes? And 8 and 2 N2, N1. That's your next one. 03 AF. And then we have two more. What's the address of Zeta? Delta word 20. Well, he's one word. It's one word, which is 3 bytes. 15, yes,
Honestly, why are we adding 300?
because it says, I'd rather you ask than flunk a test, so I'm glad you asked. Reserve word 100, so that's 100 words, and each word is 3 bytes in size. That's why. Sometimes the answers are fairly simple, which is okay, but you have to get some sense of what it is, but the bar here is not real high. All right, word, that's one word, it's 3 bytes, so we're adding 3. So 15 and 3, yes? Zero, zero, 3. All right, now the last address, we have byte, and there's 3 of them. E, O, and F are each one byte. So for byte declarations, it's the size of the declaration. It's 3 bytes, each letter, each character is 1 byte. So it's another 3. 003B5. How much space does this program take in memory? 003B5. That's the space that's required. Hex number, of course.
Yeah, so the C stands for characters.
Yes,
C.
right. With byte directive, you have a C, which is a character, or an X, which is hexadecimal. Either of those. It's got to be one of those. It's either character data or it's a number. Yes?
What's the point of the operand for delta word?
Let me see, Mr. Ken. Delta. Word 20. All right, what that says is allocate 1 word of memory and put a 20 in it. So in memory, you have this. 1 word, 3 bytes. And there are your 3 bytes. Note that that's not 14. That's 16 plus 4 is 20. Because it's space 16. Other questions? This was the easy part. Getting these addresses is the easy part. Well, the first time you do them and you don't necessarily know, oh, reserve word, well, it's 3 times the quantity. But you do now, so this isn't hard, right? I mean, it's okay. You can do this. Are you ready for the hard part? Yeah. Sure, let's grab the bull by the horns and go for it. We're going to hand translate to assembler. Now, almost all assemblers are 2-pass designs. And the reason for that should become clear very quickly. Is there any benefit to getting the addresses of everything first before you do anything else? Yeah, sure. Why? Because if we have a memory reference, we can encode it if we know where it is. But if we don't know where it is, what do? So for instance, look at the very first instruction on line 7. LDB # delta. That says load into register B the address of delta. Okay, if you don't know the address of delta, then what? What do you do? Okay, you're dead in the water. You can't encode that till you know the address of delta. That's why the first pass we go through and assign an address to everything. Then we can actually assemble these things. because now we know the address of delta. The address of delta is 003 AF. Right? Okay. Now I see, I said that you needed this sheet, but I put them on the bottom here. And these are the opcodes to make life easier. Once you have the opcodes, then you're home free. But you can check the actual format. So let's do this first instruction. The ones that have precede this, lines 2 through 6, are all assembler directives. And so that tells the assembler to do things. And we're going to talk about that as we go forward. Essentially, you have lookup tables. So you have something like OFFB EQU8, and it's just an alias. That if you have OFFB in your code, the assembler will substitute 8. So those are directives to the assembler, but the actual machine code starts on line 7. So we have LDB # delta. Okay, so let's encode this. It's format 3. Now, do we remember what format 3 is? How it looks? Let me just write a little cheat sheet over here on the side. Format number 3. We have the opcode. Then we have flags. Finally, we have a displacement. That's 12 bits. And these flags, of course, are 6. That's 24 bits for format 3. Now, last time we mentioned all of the instructions, the opcodes, are not only even, but factors of 4. 0, 4, 8, 12. That's all they are. What that means in binary is the last 2 digits are zeros. So you have 8 bits, and the last 2 are always 0. Okay. LDB is 68, so let's build this thing. LDB 68. Okay. There's your 6 bits. We start with 10, it's 8. Now the actual opcode is this. However, since those last 2 bits are always 0, we can use them for something else if we want to. So what we need here is N, I, X, B, D, E. These are your flags. So far, so good.
How did you get the opcode?
It's on the bottom here, 6-8. I put them on the bottom of the sheet.
Okay, so when we did the addressing mode instructions and you had LDA alpha and LDA pound alpha, is that being adjusted here based on Bravo, Sierra, or
I'm not sure what you're asking.
this sheet? Is this applying to this at all?
No. I mean, we're going to talk about what these addressing modes are, so it very much matters, right? But we're going to talk. So what is addressing mode N? So that's set if N equals 1. What does that mean? Indirect. This is indirect. Now, for backwards compatibility, there's a quirk. All machines have these. And so the way this works is if it's neither N nor I, both are set. So N means indirect. Well, what's an indirect? Remember, it's a pointer. So look at line number 9, the at beta. That's indirect mode, at beta. What that means is located in memory at address beta, is another address that you're going to read and go there to get the contents of memory. All right, so it's not indirect. There's no @ sign in front of it. Immediate. What does immediate mean? It's a constant. Immediate means it's a constant. The I mode. Okay, constant is a pound sign. Now, does everybody understand the difference? Pound sign delta means the address of delta. That's a constant. You could also say LDB pound sign 2. It would probably be a mistake, but you could. Let's just put a 2 in that register. Okay? Well, it's the difference between the address to or what's in memory located in address to. Everybody with me here? There's two things. So you've got this memory location. Imagine this is your memory map. Okay, this byte right here, it has an address. It has an address. That's what you get if you use the pound sign with the label for it. And then you have the contents in memory at that address. Is everybody with me? Okay. This is the actual hard-coded address. This is what we want. That's immediate mode. So it's not indirect. It is immediate. 1 is yes, 0 is no. Now again, if it's neither one, then you set both of them to 1. You set both of them to 1. And the reason this is done is to make a distinction between the base architecture SIC and the advanced SIC XE. It would always be 0, 0 with the first and 1, 1 with the second, so you can tell the difference. Okay, let's keep going. X is indexed. Well, in indexed mode, if you look, for instance, at line 15, you see alpha comma X, and there's a closer one, line 10, beta comma X. So that means go to beta and add X to it, the address. So if beta is at 2B and X has 1 in it, then you go to 2C instead and read the contents of memory there. So that is indexed. You guys may remember from CS530 Sep, we had something that looks like this. You might remember that faintly. This is an address register A2 plus 2. Go there and dereference or read the contents of memory at that location. So if A2 has an address in it, I don't know, let's make one up, 3110, then you go to 3112 and read what you find in memory at that location. Same idea with the X here. It's a displacement that adds to the base address. So it's the base address plus X. Well, we don't have that here. That's not going on here. So I'm going to put a 0. All right, so these are your basic addressing modes. There are 4 of them. Int and I are set to 1, which means it's neither one. There is the X for indexed. There is immediate and indirect. So we have examples of all of these, and hopefully when we get done today, you'll understand this a little better. Yes?
The function of n, again, sorry.
No, it's okay. I'm sure that you're not the only one that's a little uncertain about this. That's why it's a little tedious to work through this, but it helps you understand what's going on. So an example of the n would be line 9. It's got at in front of the beta. It's got the at in front of the beta. So if you have this sheet, you can refer to it, it'll be helpful. But essentially, we'll use LDA as the base. here are the kind we have. LDA alpha. Okay, this is standard indirect. Oh, I don't want to put that. That's dereferenced. So LDA alpha says go to alpha, read what you find in memory at alpha, and load it in register A. Okay, we have LDA pound sign alpha. So let me put contents from memory at alpha. Go to alpha and read the contents in memory. Pound sign alpha, the address itself. Address of alpha. LDA at alpha. And this is 2x dereferenced. The memory at alpha is
I don't know.
an address
From memory.
to be dereferenced. And by dereferenced, I mean go to the address at alpha, read it as an address, and go to that second address and read the contents of memory there. You with me?
Could you repeat that one?
Okay, let's draw a picture. I like pictures. I like pictures, they're helpful. Memory math once again. So this spot is alpha. So if we say LDA at alpha, what goes into the A register? First we go to alpha. In alpha we read the address, 2B. Then we go to the address 2B and put what we find there. I'm sorry, I want to do it this way. I don't want the extra indirection. Like this. So it gets this chunk of memory. Apologize for an extra step there. Go to 2B and read what you find in memory at 2B. And put it in the A register. So the A register now has 2. So without the at, you would have 2B. With the at, it has 2. Yes.
So the way you had it before, it would have just held the address of 4E?
Yes. Yes, I'm sorry, I'm not using my head. I was working on C++, and I had this long string of dereference pointers, and I still have that in my head somehow. So I'm actually going to wipe this out and just leave these 2 pieces. It's a simple idea. It's a simple idea. Go here and take what you find as the address and dereference it. So this says at alpha, go to alpha, read the address and go there and take what you find there. If we simply had LDA pound sign alpha, then what would go in A? It would be 2B, right? The address, 00002B. You with me? Okay. It sounds more confusing than it really is. Okay, so these are your base addressing modes. There's also the LDA alpha, comma, X. And this is dereferenced. read contents of memory and put into A. And this is address alpha plus x. Go to alpha and then move down whatever's in x, that register, that many more bytes. So if the x register, let's see. If x has 3 in it, then this would put 4e in register A. This is alpha, alpha plus 1, alpha plus 2, alpha plus 3. Go to alpha plus 3, take one word, and put it in the register. So then we would have, I'm sorry, what about 4e? Those are your modes. So a recap. The first one, LDA alpha. Go to alpha and put what you find in alpha in the register, the 2. That's the first, the most obvious, and the most common mode. LDA pound sign alpha. Alpha itself is the address of alpha. And so the address of alpha itself is loaded into A. At alpha is go to alpha and read that address as another address and go there. Go to alpha, take 2b as an address, put the 2. And finally the x, it's an offset. Yes?
What I was actually referring to is I know that the I is set if it's an immediate constant that you're looking for. The X is for if there's an offset from the
Yes.
address it's pointing to. And N is set on all of those except for the pound sign. So what is the N set specific for?
The N refers to the at, this one.
It's also set without the at, isn't it? I missed-
Well, it is,
or is
but
it-
that's the quirk. This is N equals 1. This one is I equals 1. And this one is X equals 1. This one is I equals 1 and N equals 1. So it's neither indirect nor immediate. They're both 1. Now, why? Okay, we have this other format we talked about in the beginning. We have 8-bit for an opcode, and we have a 20-bit address with the X bit, 15, 1. This is the form. So if you have this form, this is always 0, 0. And so with the architecture that we have here, if it's neither X nor 0, you set it to 1. What that means is you can never have 0, 0 here if it's format 3 or 4, if it's the XE architecture. But if it's the base architecture, SIC, then it always is. So you can never have these two 0, 0, unless it's the first primitive architecture. With what we're going to be working with, this SIC-XE, this is an impossible setting. If it's neither one, they're set to 1, and it tells the difference between this versus the SIC-XE. This is SIC. So it's for compatibility reasons. So if the assembler sees that, it goes right away, is format 0, which is SIC. So again, every architecture has these quirks. All of them do. For this one, if it's neither N nor I, you set both to 1. So it's not really a lot to remember, it's not terrible. All right, let's keep going. Okay. So, this first one, it is immediate. Now the problem becomes encoding not the address, but the displacement, the offset. Remember that the offset is going to be 12 bits, but a memory location is 20. Well, it's cheaper, faster to encode 12 than 20. So, we have two possible modes we can use. P or B. So, you can use either one as long as base is set. However, for this first instruction, base can't be set. You can't use it until something is in the base register. That makes sense, doesn't it? You can't use base until there's something in the base register. So when you load the base register, you can't use base mode. Therefore, we're going to use PC mode. All right, PC mode. How do we calculate the displacement? So the formula is displacement equals destination minus PC. And because the program counter continues to move, the formula is destination minus source plus root. Because the PC moves to the next instruction, the program counter. When it reads the instruction, it increments the program counter. Remember, the program counter always has the address of the next instruction. So you read it and increment it to the next instruction. So after it has read the LDB, it then goes to the next instruction, which is at address 3. So it increments it as soon as it reads it. So then to get the offset, it says, okay, from where the PC is right now, which is the address plus 3. So can we do this formula? Destination minus the program counter, or source minus 3. Okay, where are we going? Delta. Now what's the address of delta? 3A. Minus source plus 3. Well, where are we at right now? 0 plus 3 is 3. That's the formula. Okay, F minus 3 is 15 minus 3 is 12, which is C. Okay, we can't use base, that's out of the question. It's PC relative. And now the E is format 4. And the format 4 instruction always has a plus in front of the operator. Plus LDX. That is a format 4 instruction. Yes?
So we set base equal to 0 because in the code it actually loads something in base and then a delta?
Well, after we've loaded this, we can use base. But we can't now. Yeah. Okay. And now we have 3AC. 3AC. Is everybody with me? Yes, no, maybe, perhaps. Okay, let's regroup and write our nibbles down. This is 6, 9. Let's lock this. Two, 3, 8. That is the machine code for that first executable instruction we have. 692 3AC. CS530 Okay, is that confusing as all get out, or are we making sense? Let's keep going. We have to get a handle on this. Next instruction. Note that last semester their project was writing the software to do this. They wrote the assembly. You guys aren't going to be doing that. We're going to do a preprocessor instead. Okay, the next one is LDS 100. Okay, LDS 6C. 6C, when you're done, when we use the first 6 steps because we know the last two are 0, we have N, I, X, B, E, E, our flags. Okay, how do I want to set the N and the I? Is it indirect? No. Is it immediate?
Yes.
Yep. So they're not both set to 1. 0 for N and 1 for E, which means it is immediate. X, no. Okay. Is it base? Is it base? Is it PC? Well, no, that's an offset. It's a constant value. There's no offset involved here. So if you have your these guys, you can look and you can see. Let's see here. Where is constant? So these are the grayed out ones because this is less common. But the LDA #C, it's not base relative, it's not PC relative, it's neither one of those things. And it's not format forward. Okay, #100, that's a displacement. Everybody agreed? How'd you get that? It's 6, 4, and X, 6 times 16 plus 4. That's 100. Or if you want to think in binary, this is 1, 2, 4, 8, 16, 32, 64 is 64, and 32, and 4. This is 64, this is 32, this is 4. Add them up and what do you get? Okay. You have to convert it to hex, or binary as the case may be. We use them interchangeably. So is everybody on board? You can't put 100 there. It's not going to work. It has to be binary. So yes, you're going to have simple conversions. I mean, I think this is fair. I think all of you should know that 6 times 16 is 96. You should know that. Okay. At least not the first time you've seen it. So then when we group into 4s, get our nibbles, and we have 6, D, 0, 0, 6, 4. And that is the machine code for the next one, 6D, 0, 0, 6, 4. Is that one a little bit easier? I hope. Okay, let's do plus LDX at beta. Now the plus, and we're talking line, which one? 9? Line 9. Plus LDX means it's format 4, it has to be the full instruction. And the at means indirect mode. So this one will also be easy, there's no calculating of displacements. So we have plus LDX at okay. LDX is 0, 4. LDX 0, 4. And then we have NIX. Remember, there's 6 bytes for the opcode, and the last 2 are always 0. We're using those for the flags. Is it indirect? Yes, it is. Indirect. At sign. Is it immediate? No, it's not. X? Nope. Okay, it's got a plus there, so it's neither base nor PC relative. But it is extended, which is format 4. And then we have the full 20-bit address of beta. So, the address of beta is 00157. 0, 0, 1, 5, 7. Then regrouping, we have 0, 6, 1, 0, 0, 1, 5, 7. So it's 8 hex digits, 32 bits. Not as efficient as using format 3, but you go where you gotta go. 0, 6, 1, 0. 0, 1, 5, 7. Okay. Not too bad. I'm going to erase now. Everybody got it? Okay. Let's move to the next one. And for the next one, we have another format 4 instruction, LDA beta comma X. LDA beta X. Okay. So we have the LDA and it's 0, 0. And then we have MIX, B, D, E. It's beta X. Wrong thing. Plus LDA. Beta comma X on line 10. Okay, I think we've got it. Holler at me if I write something down that's wrong. Okay, beta comma X. Is it indirect? There's no at sign. Is it immediate? There's no pound sign. It's neither one, therefore we have 1, 1. Neither indirect nor immediate. Now, is there an X? Oh yeah. Base or PC relative, it's plus. So you got neither one of those, you got the full address. Not base relative, not PC relative, but it is extended format 4, and then we have the actual address of beta, which is 157. 0, 0. 0, 1, 5, 7, 1, 2, 3, 4, 5 digits. So 20 bits, 4 times 5 is 20. 4 digits each, 5 letters or numbers. So we have 0, 3, 9, 0, 0, 1, 5, 7. Is it getting a little better? You'll get the hang of it, you just have to work on it a little bit. This is 0390. 0157. Okay, so the next one's a little tricky. The next one on line 11, add gamma. Add gamma, okay. Okay, so this says go to gamma, read the word in memory, the 3 bytes, starting at gamma and add it to register A. So this is the most common instruction we're going to see. Add is 1-8. 1-8. Okay. This is format 3. Is it indirect? No, there's no at sign. Is it immediate? No, there's no pound sign. So both of these are set to 1. They're flags. Is there an X? Nope. No X. All right. Now we have to decide how we're going to encode the displacement. So we have gamma. And let's do it both ways. Let's do it both ways. Where is base? Oh, delta is later, so that won't work. So we'll skip that. So we have no choice. It's PC relative. Has to be. Okay, we're going to gamma, and that's 283. That's the destination. Minus the source plus 3. Well, the source is E, is it not? Address E? Yes? Where is the instruction add gamma at what address? What's the address of line 11? It's E, right? Plus 3, that's 14, needs 14. Plus 3 is 17. That would be. Note that that's not 11. That's 16 plus 1. You with me? Who's confused? Okay, the formula. We want to encode this so that it says to the CPU, go forward in bytes from where the PC is right now. From the value in the program counter, the PC, go forward in bytes and read the contents of memory at that location. Remember we talked about the fact that there's a positional relationship between all these pieces. Can we say what the distance is from the instruction add gamma to gamma? How far forward is it? How many bytes forward? Well, the address of gamma is 283. So if I subtract E, that's the distance from that statement to gamma. It's go forward in bytes. However, the program counter is incremented once you read it, so it goes past what it just read. And it reads a word. Therefore, it will read 3 bytes every time. The next instruction, if we're doing PC relative mode, it's format 3, which means it's 3 bytes. So the machine read 3 bytes. So the formula is offset or displacement is equal to where you're going, the destination address, minus the PC, or the destination address minus the source address plus 3. Because it's so the destination, the address again, minus where we're at right now, plus 3, 17. We're at 14 is the source. So the PC is down 3 more. It read the instruction. So it's 17. 14 plus 3 is 17. Again, this is not 11, it's 17. You with me? Okay, it will take a little practice. 3 minus 1 is 2. 8 minus 1 is 7. 2. Okay, we have 12 bits for the displacement. How many hex digits is 12 bits? How many hex digits in 12 bits? Each hex digit is 4 bits. 3 digits, yes. So these are my 12 bits. Now, how can you tell if the offset is too big? Because this could happen. Well, it's a forward reference, so it has to be positive. What if I had a 1 here? Too big. Too big. What if I had an 8 here? Too big. You have a range. If you have a forward branch which has to be positive, and you end up with a negative number, then it's overflow, it's too big. So what are the possible values that you could have here? It has to be positive because you're going forward, you're not going backwards. Now you could have a backwards branch. Of course you could. You could go, back to the start of the loop. But this is reading memory that's forward, and so it has to be a positive offset. It has to be. Okay, well these are 2's complement numbers. So the range of positive numbers here with 12 bits, 0 up to what? 7FF. Right? You got 3 digits. That's the last positive one. That's a 0 at all ones. You with me? That's a 0 and 11 ones. This is that's the last positive number. And the negative numbers, 8, yes? You're familiar with 2's complement, so you remember that. Starts with a 1, it's a negative number. If it's a negative number, you got a problem. Okay. In decimal, what is it? Minus 20, 48, up to 20, 47. These are the range of possible offsets in base 10. But it's just as easy to do it in hex. All right, so does this work? Is it valid? Yes. It's positive forward reference. We didn't overflow. Okay. Is it base relative? No. Is it PC? Yes. Is it extended? No. Now we have the 272. So this says go forward in bytes to find Hannah and read from memory. This is much more efficient than hard coding the full address at the end. So regrouping, we have 1, B, 2, 2, 7, 2. 1B2, 272. Next one, LDX at zeta. LDX at zeta. All right, so LDX is 04. XVE. Okay. At zeta. Is it indirect? Yes, it's the at sign. Is it immediate? No, can't be both. Can't be an X either. All right. Is it base or PC relative? Because it has to be format 3. Why does it have to be format 3? Because there's no plus in front of the LDX. Therefore, it must be format 3. Okay. So we have to figure out whether or not we're going to use PC relative or base. So for this one, we can do both, and I think we should. So let's do PC relative first, since we've been looking at that. Let's do another example. Destination, and the destination is, say, 3B2 minus source plus 3. Well, we're going to 1, 1. Yes? Okay. Yes. We subtract, cancel the B, we have A. We borrow 16, we have 2, that's 18 minus 4 is 14, that's E. You guys can do this, right? Okay. A minus 1 is 9. 3 minus 0 is 3. Go forward 3 9 bytes. And read what's in memory there. There's your displacement. So this would be PC relative not extended 3 9 E. Like so. Now let's look at base relative. Now why do we have that? Well, base relative exists because you might have a lot of storage allocation space. You might have large chunks of memory. In this case, it all fits because the numbers are small. I didn't make them too big because doing the calculations in X is a problem for a lot of students. So they're small numbers. But instead of 100, suppose it said alpha reserve word 4,000. That's 12,000 bytes. Is that going to fit in the range? 12,000 when the largest positive is 2,047. No, that's not going to work. So to get to areas in memory in storage allocation section, we have this special mode and we set the address of something as a base that we can key off of to calculate displacement. That's what we're going to do. So how are we going to do it? What is going to be the mechanism? What's in the base register? Delta. Notice there are 2 commands here to start this thing. We have base delta. And then we have load into the base register # delta. So the assembler knows what's in that register. It has to. Okay. So there's no PC going on this time. We still have destination minus the source. Well, the destination is zeta, right? 3, B, 2, and the source is the base. No plus 3 here. It's just the base. So the base is delta minus 3AF. Can you do the subtraction? I see smoke rising as the wheels spin. I hope you can. Put A there. We're borrowing 16. 18 minus F. 18 minus 15 is 3. A minus A. 3 minus 3. Wow, does it fit? But it's 3, I hope it does. Okay, so this time we have base, not PC, not extended, and then we have those are the two modes. So base only goes forward, it can't go backwards. It's not for branching. Therefore, the range for base relative is 0 up to 40, 95. 49. Questions? All right, I want you to see if you can do the rest of these. Now note that I'm going to ask you to do this on the first midterm. It's coming. And it's tempting to say, this sucks, I hate it, forget about it. And on Thursday, or Wednesday rather, we're going to start working on C++. We're going to set this aside for now and come back to it. But when you revisit this, so go ahead and now that it's fresh in your mind, see if you can finish this worksheet. Questions?
Are
Yes.
you gonna talk about class accounts?
You have your class account. You should have received. Did everybody receive one? Yes? Okay. Well, it was my intention to start on that today, but we didn't get there. I brought my laptop. Yes, well, part of the discussion on Wednesday is going to be how to connect to Edoras.